hello, you're one guy online, and we have a big audience in the room, but you can't see it. We have a session, 15 minutes presentation from a researcher from all over the world. We start with Belgium, and I'm looking forward to a presentation on artificial intelligence. We all know that we need training data, and you will show us how you create training data with very colorful point clouds. I've read your papers. It's an excellent paper.
Thank you. Good morning, everyone. I will present my training data creation pipeline. First, I will show my research group, the company we're working with. Then I'll explain something on scan to BIM, then on point cloud interpretation, and then the training data creation pipeline. Further, I will show some results of my tests. Our research group is based in Leuven. We do in Ghent of the KU Leuven. We do research in all kinds of the reconstruction and measurement techniques and the analysis and interpretation of this data. My project is, of course, in the scan to BIM field. Later on today, we will have a presentation on road construction also. Method is the company we're working with. They are one of Flanders' largest surveying companies. They are active in all kinds of surveying, such as classical surveying, monitoring, and technical measurements. But they also have a large BIM division, such as a BIM shop, and they are also active in the digital twin industry. Now I will explain something more about my research itself. My research is on scan to BIM. There are two major stages in this research, the data acquisition and then the interpretation and reconstruction of the data. In my research, we follow the approach that we will split the interpretation of this point cloud data in 3 different steps, where we will first detect and reconstruct the structures, which we can then use to further enhance the detection of architectural elements such as windows and doors, and further enrich these BIM models with appliance objects such as electricity, HVAC, and MEP objects. From prior research, we find it that when we are segmenting point clouds, such as you can see on the slide of one of our labs, that there are large discrepancies between these classifications of walls, for example. So that's why we follow the approach of first detecting the walls and structure objects. So in the rest of the slides, we will also only use these 6 classes to segment the point cloud data. Now I will explain something more about the interpretation. So scan to BIM, of course, exists out of 3 major steps: the acquisition, the interpretation, and the reconstruction of the BIM data. In this presentation, we will only focus on the interpretation of the data. This interpretation is normally done manually by a modeler that then uses the point cloud data as a background in modeling software such as Revit, and is a time-consuming task. This could be automated by segmenting the point cloud using, for example, machine learning techniques to assign labels to every point in the point cloud. These methods are data-driven and need a lot of training data to achieve the necessary accuracies. So large amounts of label training are needed. This training data can be get from online datasets. There are not as many online datasets that are labeled. One example is the Stanford 3D indoor dataset that is shown on the slides. But the creation of training data is mostly a manual process that takes a lot of time. On the other hand, we could use BIM models to create synthetic training data by sampling the BIM objects, but this results in unrealistic point clouds without noise or clutter, which shows difficulties later on. Our approach uses the point cloud and the BIM model of commercial scan to BIM projects to enhance later steps. So we use recent projects to later on use them for better segmenting the point cloud data. So this is an example. Now I will explain my approach a little bit. The proposed training data creation pipeline starts with the BIM model, such as you can see here, of 2 walls and a column. We sample points on this BIM model. We leave the BIM geometry out of it later. These sample points are then combined with a downsample point cloud. And then we initiate a raw filtering using cloud-to-cloud distances just to reduce the computational times later on. Then we will do a fine filtering per point of the targeted point cloud, where we will do a nearest neighbor search. And then on these nearest neighbors, we will compare the normals of this of all points until we find a matching normal. So if the normal is not sufficiently alike, then it is not used until we find a point that has a similar normal, and then the label of that point is assigned to the latest point. Some known problems that we already discovered in our approach, that in some cases terrain outdoors is modeled as an IFC slab, for example. In our code, we chose to use IFC slab, but the upper part, the upper surface of the slab is a floor, and the bottom surface of the slab is ceiling. This leads to misclassifications of data that is inaccurately modeled, such as can be seen here, where some points are labeled as ceiling, where they are actually part of the terrain. These are some test cases that are discussed in the paper further on. As you can see, we can quite nicely extract beams from BIM models, which is one of the classes that gives large problems when segmenting. But as you also can see, there are problems on the ceiling, on the roof of the farmhouse, where there are some parts labeled as ceiling where they should actually be. Another test case is this one, where you can see that on the top, oh, maybe I'll show it. No. So back. So here, this part was inaccurately modeled, so this resulted in some mislabeled points as clutter. Here you see that there are also large red parts in the walls, but actually that are closets. So in this case, it is correct that these are labeled as clutter objects. Finally, we used a recent deep learning network to train on this data combined with benchmark data sets. And we used the different configurations of training data. So we used point clouds with multiple floors in it and without multiple floors. And we concluded from this test that when applying point clouds with multiple floors, that there are problems in identifying the floors and ceilings of the middle floors, such as you can see here, where large parts of the floor are actually labeled as a ceiling. So then I'll jump to some short conclusions. The synthetic data cannot fully replace the real-world data, so still real-world data is needed, but the creation of this data is very time-consuming. BIM can solve this problem by creating this synthetic data, but it's not all, such as I already mentioned. But we can also use this BIM combined with point clouds to create real-world training data. And recent deep learning networks have large problems with multiple floors identifying, or the ones that we tested. Thank you for your attention.
Thank you for this really great presentation. Great. Yes. And you kept the time really strictly. Thank you. And it's interesting. We all know that point clouds are stupid as hell, and you told us that we have to interpret them. But also the BIM models are all sometimes really wrong, as you just presented, and that's important to understand, I think. Could you maybe tell us something about the computation time of your what is one point cloud of the building? How long does it take?
It depends on the how large it is, but of the building, the retired home, this one,
yes,
it took 2 hours.
2 hours, okay, that's good, I would say. Yeah.
Downsample to 1 centimeter.
And what software libraries are you using for this?
I coded it in Python, and we're using IFC OpenShell to interpret the IFC models, because we use IFC as input, and we use OpenVIDEO to interpret the point clouds and the computations.
Great. Are there any more questions in the audience about this important topic? Then I would like to thank you. And the next one is Tim in the session. Tim will present, he's from Dresden as well as I am, and he will present his PhD thesis. He is Dr. Kaiser, but we are continuing the research on VIDEO-GRAMMETRIC 3D reconstruction together with BIM. And the main problem is the co-registration, to bring the point cloud to the BIM model in the same coordinate system. And Tim developed an algorithm for this in his PhD thesis, but only with photogrammetry. And now he will explain how he does it also with VIDEO-GRAMMETRIC videos. And we just started the project. So please look at the title. The title is Work in Progress, so you will see current research.
So after Christian already told the complete presentation, I am now starting with my part. And basically, photogrammetry and BIM can be used in multiple use cases. We heard a lot of presentations yesterday that use the point clouds to create the actual BIM model, but also if you have a model at hand, we can use point clouds as valuable data source, for example, to update the current model or to monitor the structural health of the buildings, and, for example, to find and already locate cracks and damages. And in most of the cases, structure for motion is used for data capturing, but if you have the point cloud generated and the building model and you want to combine them, you will result it's something like this, where you don't have the actual transformation ready and it's not up to scale. So this means you need to have to calculate transformation parameters to correctly register the point cloud. And usually you would do this by using control points, but in our approach, we use the building model itself, because control points can be labor intensive to set up. You need additional measuring devices, and they also can become invisible during the construction process. So the building model itself defines the coordinate system that we can use to register the point cloud in. And also as we have the 3D geometry of the building elements at hand, we can use this information of length, height, and things like that to get the transformation parameters calculated. And important is also that we have semantics and attributes at hand. So not only the geometry, but we can also use these attributes to filter out objects we want to analyze. And the basic idea is the following, that if you imagine an indoor scene, you have orthogonal spaces, orthogonal surfaces that constitute the room. We have the floor, we have orthogonal walls and the ceiling. And these can be parameterized as planes, so they have a vector, and we have the distance to the origin of the coordinate system. And from the images, we can extract 3D line segments that are lying on these planes. And using geometric relationships between these two data sets, we are able to calculate the transformation parameters. So per one line plane pair, we get two observations. The first one is that the direction vector of the line segment must be perpendicular to the normal vector of the, and the second one is that the fully transformed midpoint of the line must be placed inside the corresponding plane. So we have two observations per pair. That means we need 4 pairs in total to calculate our transformation parameters. We are doing this by using a Gauss-Helmholtz model and a classical least squares approach. So to sum it up, we have two input data sets. On the one hand, the 3D segments. We are using a tool called Line 3D++, so that was not developed by us, but this is capable of retrieving the 3D line segments based on the oriented images. And the segments are parameterized with their starting and endpoints in the coordinate system of the SFM reconstruction. And on the other hand, we have our building model here in IFC standard. And especially we are using IFC space and space boundary classes to filter out the corresponding planes on the bounding surfaces. So here you can see the overview of the developed approach. On the left hand, we begin with the images, perform structure for motion so that we get relatively oriented image blocks and also the point cloud. And then from there on, we can calculate the 3D line segments. On the other hand, we have the BIM model where we specify the rooms so that we don't have to compare the complete model because it would be too time consuming and too many planes would be generated. So we can use the semantic information to limit the region of interest. After we have these two data sets ready, we go to the blind plane matching, where we use some kind of Romanschek algorithm to establish the correspondencies. Then we need to calculate good approximate values because due to room ambiguities in the rotation, we have to have good initial starting values. And after we have these, we go then finally to the parameter estimation. And afterwards, we check which parameters are quite good. And then we have these parameters at hand to transform the point cloud into the building coordinate system. So what we are currently now doing is we want to replace the single images to videos, and then perform the structure for motion approach. And we need to enhance our matching algorithm because it was shown that it's not for the complete automatic registration. It's not robust enough, so we need to put some effort here. And basically, the matching algorithm is the crucial point of the complete procedure because we can only calculate correct transformation parameters if we have correct line plane pairs. So if we have a line that's actually not on the correct, located on the correct plane here, we can't calculate correct transformation parameters. And this is quite difficult because we don't have any prior knowledge about the distribution of the line segments. So a human might understand it with a human scene understanding where the lines are belonging to, but the computer has no chance because he has no idea where to go. And one could think that we can just calculate all the combinations, but this would be too computationally expensive because there are too many combinations of line plane pairs. So we need a different approach. And to do so, we first calculated the main axis of the 3D line segment. So here you see the reconstructed room. And here the reconstructed main axis based on principal component analysis in green, blue, and red. And after we have the main axis, we can calculate for each segment if it's parallel to one of these axes. And afterwards, if we have set it that it is parallel to, let's say, main axis 1, we calculate the distances from the midpoints to the other main axis. That means we get a one-dimensional distance vector, and then we use the Chang's natural breaks algorithm to cluster these distance values. And the idea of this algorithm is to find clusters of same distance. The algorithm tries to minimize the variance inside these clusters, but also trying to maximize variance between clusters. And as a result, you can see here we have separated the lines for each coordinate axis. So one for the x-axis, one for the y-axis, and also for the elevation, for the z-axis, for the height. And combining this, we can better classify the segments to the corresponding boundary surfaces, and from then on continue with our Ransec matching, and do the same procedure that we have developed before. So now the third title also said we want to use videogrammetry instead of photogrammetry. And why do we want to do this? Because we want to further ease and simplify the data capturing process, so that also users from other domains like civil engineers or other people can also make use of our approach to concentrate on their later analysis, because, okay, we calculate transformation parameters, but we do this for some specific purpose so that people can focus on the actual analysis. And videogrammetry basically is photogrammetry plus an intelligent image selection from the videos, so that we can split the videos into keyframes and then perform our structure from motion approach with these extracted keyframes. And in this context, we also came up with a new use case, namely structural health monitoring. And as you could see, we developed our approach mainly for indoor scenes where we have orthogonal boundary surfaces, and we could make use of the special IFC structure with space and space boundaries. But in the case of bridge monitoring, this becomes a bit more different, because IFC in the infrastructure world is not very developed. It's in the early beginnings of standardization. So it's a bit harder when we have the BIM model and the authoring tool to export it to IFC. We will lose some information, but we will see that later on. Yes, and here now you can see my two colleagues walking around with the GoPro around the bridge, capturing the image with a gimbal lock mounted to the GoPro, so that we have some good stabilized images. And then after selecting good keyframes, you can see here the reconstruction of the bridge and the used images, the dense point cloud, and here are the extracted 3D line segments. And what you can already see here is that we mainly have vertical segments and not so much horizontal line segments. This results of the uniform capturing height. So we didn't change a lot in elevation during the capturing process, which is resulting in very few horizontal line segments. So after our first test, we noticed that, so we know that we have to go out in the field for additional time, and also maybe combine the terrestrial capturing with some drone overfly to also have it from different elevation perspectives. And as I said, one of the difficulties is when it comes to the IFC export, because the BIM authoring tools are not yet capable of modeling infrastructure projects very good. So when we export it to IFC, we lose all the pretty good information we have in our BIM model. It becomes let's say, stupid 3D mesh model instead of nicely modeled CAD planes or surfaces. And also we lose the semantic information because it's just exported as building element proxy. So this could be everything. So to sum it up, we could demonstrate that the basic workflow can also be used with videos as data source, whereas the bridge test showed us that we have to kind of optimize the complete capturing process and to use also drone imagery to get a more complete reconstruction. Then we want to make or test our approach based on first on manual assignment of line plane pairs, because that's easier to establish correct correspondences. So not the entirely automatic matching process, instead use manually assigned line plane pairs to in a first try calculate the transformation parameters. And all in all, we also want to enhance the complete pipeline by using a web interface, would be the ultimate goal. So the user just has to upload the video and the BIM model, and that all the computation is done on the server, and he just gets back the transformation parameters to then further analyze the correctly registered point cloud or the image block. So that was my presentation. Thank you, and I'm sure you have questions.
Yes, very interesting and very well presented talk, and interesting topic, I think. But since I'm the co-author, I should maybe ask you if you have questions on this very special approach of co-registration. Yes, please. Maybe you can take the microphone so that everyone, also online.
Yeah. Thank you very much. I would like to ask you about the coordinate systems. When you presented the indoor, yes, the BIM model and the point cloud, yes, are you using some general coordinate system, or it's only the separate coordinate system for the building?
Yes. It's a building coordinate system. So this approach is not tied to real world coordinate system like BGM or something. It's focused on the building, local building coordinate system. But if the BIM model is properly geo-registered, you also could then go from the local registered point cloud via the correctly geo-referencing to the real world coordinates. That would be possible, but in our approach, we use the local coordinate system for first re-registering.
Thank you very much. And the second question is about the accuracy. Yes, because you presented that you can use the point clouds and the imaging, yes, of the buildings for the documentation of some cracks, yes, in the facade walls and so on. What's the accuracy? Are you able to use also this technique for the documentation of the development of cracks? So when you take the pictures, for example, every month, yes, so are you able to document also the small fissures also in the walls or not? Yes, because it's a little bit how to say, the problem is in the image sensor, yes, because now they are developed very, very large image sensors, and when I will compare, yes, your the point clouds and images, yes, by the static image sensor, static pictures, yes, and the video, yes, so the video when it is in a 4K format, yes, so it's, I think, very rough, yes, for the documentation of the small, very small fissures in the wall. What's your opinion? Yes,
I mean, if you're close to the scene, you also get high resolution pictures from these small little cracks. But you mentioned accuracy. For this, I admit it's a favorable room for us because it's pretty small and pretty uniform. We have 6 boundary surfaces on top and bottom on the 4 walls, but we got registration accuracies of 3 to 5 centimeters here for the automatic construction, and for the manual there I think we were it was between 1 centimeter and 3 centimeters, so a bit better still. But also we have to say that the complete accuracy is depending on the quality of the BIM model. If you generate, and in this case we made a BIM model from an existing building, of course, so you won't have discrepancies here between model and reality already, and this continues later on for the complete accuracy or the registration accuracy. So yes.
On the resolution of the images, it's more the resolution of the images, and as Dr. Kaiser just said, you can achieve any resolution that you want with photogrammetry. As closer you get, as a better sensor you use. This is, of course, yeah, but I think this is independent of our registration approach. Yeah, but interesting. We have funding for the question you just asked. We have funding for this, so we have 1 year, and we will analyze it. And we will get back to you. Okay. Are there any more questions? We are exactly in time right now. If not, we stay orange. We have this, so we have to keep this ugly orange. We are forced to use our slides design. And the next presentation is from a research project from our university also. about construction progress monitoring, and a very similar topic. Also, we think about the co-registration. So using a model to bring the point cloud in the coordinate system of the model. But another sensor and other BIM models. And Felix, he is a research assistant since 2 years. So
my presentation. The title of the presentation is Co-registration of TLS point clouds with scan patches and BIM-FACES. The co-authors of this presentation are Enrico Romanschek. He is also a scientific employee from the University of Applied Science in Dresden, and Daniel Wujanz from the Technet in Berlin. They develop, among other things, the software SCANTRA for automated registration of point clouds with the help of identical planes and points. And as the last author, Professor Clemen, already got to know as keynote speaker. First of all, a few words about our motivation and the question, what are TLS patches? On the one hand is a BIM model, and on the other a laser scan point cloud. And registration is necessary to calculate the transformation parameters for the individual scan station. And this allows to calculate a complete point cloud. And now there are various use cases for which a comparison between point cloud and BIM may be necessary. For example, the construction progress monitoring. And for this comparison, both datasets must be transformed into an identical coordinate system. In practice, mostly current control points are used, which are measured and create reference in the BIM system. If another model is used instead of the control point, the term co-registration has recently been established. And there are various methods. For this, on the one hand, there is a point cloud to point cloud registration. Here, overlapping areas of the datasets are iteratively adjusted using the iterative closest point algorithm. For this algorithm to be successful, a good pre-orientation is necessary. For high precision engineering surveys, artificial target marks, so checkerboard marks or reference pairs are used for registration. And this procedure is currently the most frequently used one. However, the prerequisite for this is the placement of survey markers and an engineering survey, which requires additional equipment, so the total station, and also time and cost. And a complementary of even substituting approach is possible with natural primitives on the surveyed object. In general, this approach detects various types of geometric primitives from the point cloud, such as corners, lines, planes, cylinders of both spheres, and compares their positions to each other to create a link. And the natural target supplement or replace the marked fixed points and can be automatically extracted from the given point cloud. Use of natural target alone would lead to a relative registration. And for core registration, the point cloud must be transformed into a superordinate reference system. This is done with the help of thermatically measured checkerboard marks or control points. And if the BIM model is available, these planes can also be linked to detected planes from the point cloud. And the plane-based registration of point clouds from terrestrial laser scanning is successfully used in practice with high accuracy and quality assurance. And based on this, we present a special co-registration approach that makes use phases from the BIM models. And most buildings have a large number of planar phases, so it is appropriate to use phases from the BIM. For our research, we use the software SCANTRA. In the software, patches are detected from the point cloud at the beginning. Here are colored plane sections in the figure, and they were called patches. Now we want to look at the workflow. The building has been planned and the phases can be extracted from the geometry. The building is converted into reality, and at the construction site, scanning is carried out. And in the point cloud, patches are detected, and then the co-registration of the point cloud is done with the help of a handful of extracted phases from the left side, from the BIM model. And now we will look at the individual steps in detail. Meanwhile, the following question will be answered. What are the benefits of using phases instead of control points? How is the engineering coordinate reference system defined with planes? Which building components suit the novel approach, and which accuracy is achieved for the co-registration? And the question is documented. In the first step, during the extraction, each BIM phase receives a unique identifier, a 3D point on the face, and a normal vector. And the unique identifier is required, for example, to visualize calculation results in the BIM software. In our current user interface, just a few planes must be named uniquely in order to be identifiable in the registration software. And all other phases are named programmatically. And in the figure, tiny planes have been arbitrarily named according to their color. And it is important that at least 3 approximately right-angled BIM phases are selected. In order to avoid a rank deficiency in class squares adjustment of the registration. And in the right part of the figure, there are the BIM coordinate original is visible. And the BIM coordinate system is aligned to the intersection of the wall axis. And with our current implementation, the building axis must be parallel to the coordinate axis. But this is often most the case and common for new buildings. And in the second step, patches are detected from the point cloud. In contrast to other methods, the plane detection in Scantra is based on reduction to a 2-dimensional problem. For this purpose, an identity image is first created from the unstructured point cloud, and the entire data set is then divided into subset of equal size using Crotry-based index structure. And all points or observations of a single patch should lie on the same geometric plane. And if any of the observations are the subset failed the model test, the current set is divided into 4 subsets of equal size. The procedure is repeated until all observations within a subset pass the stochastic model test. And at the end of the procedure all planes of a scan with their individual stochastic properties have been determined, and the original point cloud of the scan are no longer required. And the detection of patches can be parameterized depending on engineering use cases or scanner hardware, object surface, or distance by the following parameters: a maximum point cloud to be read per scan, maximum number of planar planes per scan, limit for planarity, and the minimum number of scan points per patch. And here you can see the transition from the point cloud to the patches. In the right figure, the patches were colored depending on whether they were, so walls, ceilings, or floors. And this is how the normal topology looks in Scantra. The circles are scanner positions, and the lines show the quality of the connections between 2 scanner positions. Each scanner position has the detected patches and the presentation as a colored panoramic image. And from the perspective of the registration software, the digital building model becomes nothing more than a TLS standpoint. The term virtualization is used to illustrate that perspective. The patches also need an identifier, and the value of the translation from the origin must be specified. And this value can also be negative. And finally, it must be specified whether the normal vector of the BIM patch is positive or negative. After creation, the virtualization can be added to the observation topology. The connection to at least one TLS station must be manually created, and after that, the procedure is the same as for TLS registration. This means that each connection to the virtualization must be considered individual, and the patches in the image must be assigned to the name of the BIM-FACES. And for one connection, at least 3 plane pairs must be selected manually, and the remaining plane correspondences are found automatically by the registration software. And after completed matching, the co-registration of the point cloud to the virtualization system can be calculated. And in the upper left corner, you can see the origin of the coordinate system. It is the virtualization, and at the same time, it's the origin of the coordinate reference system. So the quality of the co-registration can be reached from the Scantra protocol, which also allows errors to be excluded. This figure shows the connection to the virtualization in a part of the protocol. The total point cloud is not distorted in itself, but positioned as best as possible between the planes. And please note that the maximum residual is approximately 2.5 centimeter, which complies with the expected deviation between BIM model and execution of construction work. And the virtualization was connected to total 7 stations, which are well distributed in the building. And this in turn means that there are no major deviations between the model and the reality. And this is the result. The figure shows the original BIM model with the registered point cloud loaded. And the quality depends on conformity of model and reality. And the amount of data is considerably reduced with losing important information from the point cloud. In addition, the point cloud, the patches are also co-registered at the end, and the presented approach will be used in further research on highly accurate construction progress monitoring that fulfills geodetic standards. So that was my presentation. I hope you were able to understand our approach and the future benefits of that.
Yes, thank you very much for this interesting topic again. Oh, that's a good idea. Very good. Are there any questions in the audience or maybe online? Please. I'll bring you the mic.
Thank you for your presentation. I'm just not sure that I understood everything correctly. So basically, what you are trying to do is to register all these scans separately per partes. We are not like using the whole scan. Like when you got multiple scans inside the room, you are not registering them together and then trying to find the patches and align them or transform them to the BIM model. But you're doing the transformation for each scan separately?
No, it's in one block adjustment. And in the software, it's this, also the relative registration and the co-registration in the same step.
Okay, so you are using the whole scan data to transform afterwards.
Yeah.
All right.
But your question is important because we don't take the point cloud as a block, but we keep the information of the individual point, standpoint.
So you are finding the patches on each of the scan, then trying to find the pairs or the common ones between those, and for each find the transformation matrix.
Yeah, in a block adjustment. So
okay. Yeah. So we are trying to minimize the error. Okay, then I understand. Thank you.
Sorry, finding the best fitting model.
All right.
And this research is funded by the Ministry of Economy. It's not really academic research, so it will be go to the market maybe next year. So
Yeah.
this is really product development.
Yeah, but the idea is to minimize, like, or try to eliminate the error of alignment of these scans to each other.
Exactly.
All right. Thank you very much.
Are there any more questions here? Or comments or critique? Okay, thank you very much, Felix. We are in time. And what is with the next presenter? I think this will be a video. Am I right? Okay, you already started it in between. And we'll change the topic right now. So we'll go outside. We had building models, and now we go to infrastructure, to railway infrastructure from Milano University, Technical University of Milano. And interesting work how to combine geodata with civil, Autodesk Civil 3D.
Good morning, my name is Manuel Garramone and I'm presenting the paper A Multiscale BIM-GIS Framework for Railways Asset Management. The paper is divided into 5 macro sections that are Introduction, State of the Art, Research Project, Case Study and Conclusions. And now I'm going to show briefly each section. The issue of climate change and the new urban challenges have led many countries in the world to adopt specific policies. The Sustainable Development Goals, approved in 2015, are a call for action by all countries to promote prosperity while protecting the environment. The European Green Deal plans to make Europe's economy sustainable, reducing greenhouse gases emission at least 55% by 2030 and being the first climate-neutral continent by 2050. Transport consumes 1/3 of all Europe's final energy, so one of the main challenges is to reduce transport emission. The graphics show that rail is sustainable and it can play a major role in achieving the decarbonization target. Moreover, the number of people taking the train is growing, and it is demonstrated that a more investment in rail infrastructure means a greater number of users. In Italy, regional railways transport, used largely by commuters, need a management strategy. For most of them, in fact, are necessary different intervention works such as railway track adaptation and electrification. The key to handle the problem of renovation and management of regional railways is the digital transformation. In particular, the focus is to test the potential of a building information modeling and geographic information systems integrated system employed to manage this type of existing infrastructure. The starting point of the research was to investigate the state-of-the-art of BIM-GIS integration for infrastructure asset management. The analysis confirms that the topic is gaining momentum and also that asset management is supported by GIS or BIM tools, yet a strong link between the two tools cannot be identified. The articles were also analyzed considering the asset classes and the asset management functions. In the case of BIM-GIS integration, the most addressed asset classes are roads and electrical energy networks. The employment of methods based on BIM-GIS integration indicates a tactical operational characterization of this approach. The review allows also to identify some knowledge gaps related to data management, interoperability and integration, and process and service management. No references were found about railways asset class. The general objective of this work in progress research is to develop a BIM GIS framework for the regional railways management. The first stage of the framework was the analysis of the general topic state of the art to define the specific topic. The second stage of the framework, the digitization of the infrastructure, comprises two main steps, the railway analysis and the creation of the digital model. The third stage, the most delicate, involves BIM GIS data integration to evaluate possible interventions and manage the chosen one. Due to their different nature and modeling approaches in terms of semantics, geometry, and level of details, the integration is a complex task and there is no optimal conversion between them. The principal integration methods are based on exporting data from BIM to GIS, integrating GIS data into a BIM system, or integrating both BIM and GIS data on a third-party platform. Thanks to the cross-domain information specific to each railway component, it will be elaborated a more efficient asset management system. The process of the research framework follows a top-down and multi-scale approach. First, the context reconstruction using GIS layers. In this case, you can see the contour lines of the terrain and the railway center line. Moving on, the railway is described as a collection of different elements, and at an higher level of detail, each element, fasteners, rails, sleepers, is classified and modeled. The case study considered is the Ferrovie Appulo-Lucane Railway. It is a single-track, narrow-gauged and not electrified railway track in the south of Italy. The track has a total length of about 190 kilometers and it connects three major cities, Bari, Potenza and Matera. Different data sources were considered in order to build up a database as comprehensive as possible. The GIS software QGIS was used to elaborate and analyze the data. Here you can see the three principal stations in yellow and the position of all the stations and stops. The use of data from three geoportals led to have different attribute tables. It was necessary to standardize the data to have the same level of information. As a guide was used the Geographic Databases document published in 2015 by Agenzia per l'Italia Digitale, which contains a list of specifications for the identification of special data. Standardized data allows to analyze and classify physical rail elements. GIS rail line was transformed in a linear schema. Each line was then divided by type of element: point, elements, station, stop, level crossing, terminal, and switch, and linear element at ground, bridge, tunnel, and underpass. A specific code was used to identify the elements. In this table is reported the overview of the rail elements. GIS data were connected into the civil infrastructure software Autodesk Civil 3D to start with the model. In this case, the topographic map and the railway line, the one in yellow, were used as a base to create the model. A narrow-gauged general section was set for build the rail corridor. The geometric model is in progress because the idea is to add details such as sleepers and fasteners, maybe using Dynamo in order to automate this process through the visual programming language. Close to geometry there is the information. In the slide are reported both the GIS properties with the examples of a tunnel and a station, and the BIM properties. In this case, two different property sets were created. one for the FAL service chart key performance indicators, that are number of maintenance works, both scheduled maintenance works and unscheduled maintenance works, and one for the reliability, availability, and maintainability analysis. This type of analysis gives probabilistic values about the overall level of service of an item, and the indicators considers dependent events, the story of the items. There are different ways to calculate these indicators, and they depends on the available data. In this case, were used the quality indicators taken from FAL service chart from 2015 to 2019 and management system documents. In conclusion, considering the literature review, the decarbonization policies, and the social aspects, the idea is to integrate the two technologies, BIM and GIS, to handle the problem of renovation and management of regional railways. The basis is the digitization of the railway components, the process of converting information into a digital format. Each of them has geometric data, non-geometric data, and geographic data. The aim is the construction of an integrated system that can be used across different phases of the process. A federated virtual model used as a single source of truth for the project. In this way, the use of BIM GIS framework and the possibility to have model details and context data can support decision-making processes in the operation and maintenance field at a macro and micro level. Thank you for your attention.
Also, thank you. Maybe some applause. I'm not sure if you can hear us or if you can answer.
Yes, I am online.
Yeah, hey, great. I can hear you in the room. That's nice. Thank you very much for this interesting railway presentation from Italy. I just start with a question. You said you want to use Dynamo with Civil 3D. And is there a dedicated plugin for this, or are you using just the DWG files in Dynamo?
In this moment, I'm trying to use the DWG file in Dynamo, and I'm trying to add some details to the railway, but I'm testing different possibilities.
Yeah, and have you ever tried to work with Revit models? Let's say for a station, if the station is delivered at, or a tunnel or a bridge is delivered as a true BIM model, because Civil 3D is not really, it's a half BIM, I would say, half BIM, half GIS. Have you ever tried this?
Yes, I'm trying to develop some specific details, like, for example, a bridge and a tunnel into Dynamo, in order to have a real BIM model for these elements, while for the entire line, I want to try to use Civil 3D, Autodesk Civil 3D.
Yeah, because Civil 3D is supporting coordinate reference systems. That's a good thing. Do you have and did you have any issues with the coordinate reference systems? I guess Italy is a federated state, and you maybe have hundreds of coordinate systems in Italy, I guess, as we have in Germany.
Yes, now I'm using the WGS 84, and the coordinate system. I used the coordinate system from the GIS data, and I imported it into Civil 3D in order to have the same coordinate system and to have the same reference for the data, both the GIS data and the BIM data.
Okay, thank you. Are there any more questions online or in the room about this? Yes, one question. Yes, please wait. Pass the microphone.
So I would like to ask you, how did you transfer the data from the archive data, the old data, old maps and so on, to the new digital model? Because my opinion is when you have the data collected in some coordinate system, and for example, in Czech Republic is the Cartesian coordinate system, yeah, which has some specific the values, yes, of each point, yes. And I am when I am transferring these data, yes, to the WGS84, so it can be with the mistake up to 30 centimeters, yes. And in some cases, it should be very, very crucial, yes, for the BIM model in detail, yes, from the regional to the detail, micro scale. Yeah.
Have you heard the question?
Yes. In this case, I'm using the shape file to add the cartographic data to QGIS and also into the WGS, into Civil 3D, because Civil 3D is able to read the shape file. So I'm using this type of file, but the real challenge now is to try to export this model and this information into, for example, the IFC format, that is an open format, in order to share the data and information with an open standard. So this is now the problem, but using in the first part of the work, the shapefile, it's not a problem for the reference system, because it's the same file that I'm using both in QGIS and in Civil 3D.
I think it depends on the use case.
Yes.
You don't care if you have 40 centimeters displacement because you have a special use case, and then this is totally okay. But if you go to the construction site, 40 centimeters
Yes.
would be too large to strip
Yes.
the difference.
Yes.
Yeah. So it's depending on the use case, as always. Yeah.
Yes.
Any more questions? Then thank you very much again for this great presentation.
Thank
And
you.
then we have, bye, wherever you are. And then I think the last presentation, is he online or is he here in the room? Michael from, I think, this university. Okay, that's a pity because it's a very nice paper he delivered. He should present on his PhD he's currently developing, and very interesting topic. Well, maybe you all should read the paper, but we will see no video, and then the session is over, right? Yeah, we made it. Thank you all, especially the speakers here in the room and online, and as a video. Thank you very much. And now we get a coffee break. Bye bye.